Hope you're enjoying the rain here. I mean, so I understand you have come from different backgrounds, and this takes a little bit of. Okay, I suppose should be okay. So you are from. Your background is undergrad, late undergrad, early MSc. Is that correct? For all of you, right? So that's what I'm going to pitch my lecture at. I mean that it's a little bit of struggle for me also to just give 2 lectures on this subject. Normally there is a full course, and the material I'm going to cover today is generally covered in a slightly longer span, maybe 5 lectures. I'm going to do it in 2. I'm not going to go fast. I've just picked my topic such that I can tell you about the main concept here without using the formal language, because as you grow older you will use more formal language to describe the same things, and of course there is more information in more formal language, but for today's lectures I want you to get the basic concept of what we are dealing with. So my lectures will deal with radiation, and I'll talk about 2 things actually about radiation. One is description, how do you describe radiation, and the second is one topic I have picked for today's lectures, which is what I'll call thermodynamics of radiation. So how do you describe radiation, and you may ask what does it mean to describe radiation. So suppose you have a body here, it's emitting light, and there is a telescope here which is receiving it, and right in the beginning I could have given you an example from the lab, but I will not, because we are doing astronomy here, right? But all the examples I'm going to give you can all be mapped to a similar example, more local, right? I'm going to give you a more global example, because that is the setting we are going to deal with here. We are going to do astronomy here. That's our main focus. So light is coming from here to the telescope, and again I've drawn straight lines. One thing that happens in astronomy is that light can in most cases be treated as a ray. You may have read about it, right? By the way, if you have any questions about anything that I say, please stop me right there. Don't wait until the end. Just stop me there, we can have a conversation and we can move on. So please do not hesitate, right? So in astronomy, what happens is that you know light is an electromagnetic wave. You know about this, right? You have studied this in electromagnetic wave. But one thing that is less talked about is the ray approximation of the electromagnetic wave. See, you know about rays, where everybody thought lights were rays before electromagnetic theory. But then ray is a good approximation in many, many cases, right? Can you tell me what cases would that be? Somebody from the class.
Where light is considered a ray?
Yes. No. Under what approximation do you think light can be treated as a ray and not as a wave?
When the characteristic length of the system is much greater than the wavelength of light.
Did you get that? Fantastic. Very nice. Yes. When the characteristic length scales in the system are much greater than the wavelength of light, which obviously happens in astronomy, right? The characteristic length scales are typically far, far larger, right? You can see far away, right? Megaparsecs away. I'm not going to describe all the length units to you. You can work it out yourself. And the point is, mostly there are applications in astronomy where diffraction is important. Like, I mean, lunar occultation is an example of that. You can read about lunar occultation. People used in radio astronomy. So there are examples, but there are very few examples. Most of the time, the light can be treated as a ray. It's a straight line. So I'll draw straight lines coming towards us, right? As if it is a ray, right? And that works for us because the length scales are indeed far, far larger than the wavelength of light that we are going to deal with. Now, what would be an appropriate description of light? Appropriate description of light would be one in which the light that is coming towards you, right? I need a quantity that changes only when something either absorbs it. So there is some other medium here which can either absorb it or re-emit in the same wavelength, right? So maybe that it's at a certain frequency. The light is coming at a certain frequency or range of frequencies, right? You understand the concept of frequency, right? So there is some blob in the middle, and it is emitting at the same set of frequencies as the background object, or it can even absorb, right? So let's define a quantity which only changes when something is either emitted or absorbed. Free propagation, that quantity is conserved, right? Let's try to define that quantity. So let me consider a very simple geometry, and you can easily generalize it to more complicated ones. Let me take an object here. So this is the emitting object which is emitting. Let me call it as sun. Let's have a telescope here which is intercepting this light. Very simple geometry, right? You may say, oh, you have drawn a sphere here. What happens if it's not a sphere? All of what I'm going to say can easily be generalized to other cases, and I've not drawn a great sphere either. So I'm sure all of you can draw better than me. So please bear with me. So one thing we want to know is how much of the light is intercepted by the telescope. Let's first compute that. Simple, right? So what characterizes sun, for instance, is the amount of light it emits per unit time, right? Do you know what that quantity is called? Amount of light that is emitted per unit time. Astronomy we call by a certain name. Do you know what it's called? It's called luminosity, right? Luminosity is the amount of energy that is emitted per unit time. That is what we call luminosity. So sun has a luminosity, okay? Now we want to know how much energy is actually intercepted on Earth, right? By a telescope of a certain area, let me call it dA. Fine. So tell me how much light that is emitted by the sun is intercepted by the telescope. Let me call that energy dE prime. So per unit time, so in a time dt, it will intercept this much. Is it? No. This much of light is spread over. All right. So how much is intercepted by the telescope? Louder. dA prime, it should be proportional to dA, right? Which is the area of the telescope divided by. Everybody happy with this? Simple. This is the amount of energy that is intercepted by the telescope. Unfortunately, this quantity is not independent of distance, right? It depends on how far the object is, right? Correct? Using this simple construct, I can define a quantity called flux. And flux is, and I'm going to put a nu here just to indicate that we are not doing an experiment at all wavelengths or all frequencies. We are only doing an experiment at a handful of frequencies, right? So what we do is we also put a d nu here. So I will have the habit of doing it later. It will make no difference to what I am going to say. So please bear with me. I'll just introduce it as and when I feel like it. Okay. So F nu means in a range of frequency. So this quantity is luminosity 4 pi r square per unit frequency interval, right? Per unit frequency interval, I will sometime introduce, sometime I'll just remove it. Okay. That means if I multiply by the range of frequency in which the observation is done, this will give me unity, right? So that is what's indicated by nu. So I'm going to do an experiment only in a certain frequency range. So I can define this quantity called flux. You are aware of the quantity flux. This is what we measure, right? If you take a bulb and you try to do a measurement, that's what the quantity you will measure, right? Because that is what your, so you have a detector right here, and the detector has sensitivity to time. It will integrate the signal. You will keep looking at that bulb, right? Over a time dt, it will integrate the signal. That would be your LDT, and it will have an area which is something, and it will intercept that much over a period of time. Based on that, I can define a quantity called flux. This is called flux from the source, right? And you guys are used to this flux from the source. But this quantity is not suitable for us. Why? Well, because this still depends on distance to the source. Can I construct a quantity which doesn't depend on the distance to the source? Well, I picked this geometry very carefully just to compute that kind of quantity. You see, one thing I assumed is that the flux is coming from all over the surface, right? So this telescope could be actually getting flux from this part of the area, right? Maybe not from the other, maybe this part, okay? But let's try to see if the telescope was constructed such that it only got light from a part of the sun, not from the entire illuminated surface on this side, right? Possible? I'll have to make a larger telescope for that, but it's possible. So let's say I'm getting light from just a small area, which is, let me call it dA prime, right? Now let me put another thing to the geometry. Let me draw another sphere here and complete it, right? By the way, the area of this sphere is the same as the area of the other sphere, right? You understand, right? If I center it here, you will say, oh, you didn't center it at the center of sun, but it's okay, right? These are fine things, I can redefine them, but you got the concept, right? So if my telescope is such that actually it resolves the source, this is called resolving the source. When you go out and look at the sun, you see it as an extended object, right? There are only two objects in the sky you see an extended object, sun and the moon. Everything else looks like a point source, doesn't it? Right? And how do you distinguish between planets and stars? Twinkling. Why? Why? You're right. Huh? Sorry? Turbulence in the atmosphere is correct, but why stars actually undergo that and planets don't? Is it far away? Huh? Is what?
It's more far away than planets.
It is further than planets, true, but is that the reason? See, as far as our eye is concerned, you look in the sky, a planet looks like just like a star, doesn't it? Right? But you tell, oh, this is a planet, this is Venus now, it's not twinkling, right? Star twinkles. You see, the intrinsic angular size of the star is actually much smaller than of a planet. Our eyes can't resolve it. Intrinsic size of a planet could be an arc minute, while of a star, it is sub arc second. So, twinkling depends on how large the intrinsic size is, right? So, it is the smallness of intrinsic size of the star that makes it twinkle. But the problem is our eye can't tell between star and because our for us, right? So, this kind of an experiment, to do this kind of an experiment with eye, we mean you are looking at either sun or you are looking at moon, nothing else, right? But let us now see how much light is intercepted by the telescope from a small area of the sun, small area, right, a fraction of the area. The total area from which the light is coming could be whatever, it could be some A prime, I am only intercepting a small part of it. Let me put this here. This is correct, the total area from where I could have received, right. Again, you know, this is now a very subtle concept already. Using one telescope I can't do this, right. I am using multiple telescopes for doing it, right. One telescope has a fixed angular resolution, right. If I take one telescope and look at it, it will have only get it from one size, right. So, there is A prime is not defined that way, right. But if I have multiple telescopes for what we are called, what are called interferometers, about which you might hear later during the course, you can do that actually. So, I am assuming here you have multiple scales available to you. So, this is the amount of energy that is intercepted from a small part of this, right. And I have drawn this sphere to indicate the following, that I am actually intercepting a small solid angle of this sphere that is drawn with the telescope at the center. Is that clear to you? And what is that d omega? What is the solid angle that I am intercepting from the source? Which is obviously proportional to dA prime divided by
4 pi.
it's not 4 pi, it's r square actually,
Okay, yes.
right? Correct. This is the solid angle that the telescope is intercepting from the source, right? So, let me do a bit of jugglery, multiply r square here, multiply r square here, right? What does it give us? L dt dA 4 pi r square d omega by A prime. This r square and this r square cancel, right? Can you see that? There was this r square in the denominator. One r square get absorbed in the definition of d omega, the other got cancelled. Fine with you? It cancelled, right? You saw it. Now we are looking at a quantity which looks much more appealing, right? Let me write it on this side of the board now. Yes, go on.
R square gets cancelled.
Yes,
And another R square will go into the definition of d omega.
that is.
Only R square.
Sorry. Yeah, mistake. Thank you. There is no r square here. Yeah, absolutely. I thought I had cancelled it, but I rewrote it. Good. Be alert. So now I'll rewrite this quantity. Let me call it d prime, which is L dt dA, which is the area of the telescope, divided by A prime, which is the area of the source from which I would have intercepted light, d omega. Fine? Correct?
4 pi.
And there is a 4 pi in the denominator. Correct? 4 pi is also there. Fine? Now let me define a quantity and I will call it I nu, specific intensity. Like I said, I will put news here because I would have done a per unit frequency interval here. So I have just introduced per unit frequency interval did not play a role in what I am going to do. So I will just put I nu, right? And let's look at this quantity. This is amount of energy that is intercepted per unit time, per unit frequency interval. I will put frequency interval now. Per unit area of the telescope, per unit solid angle of the emitter. And this quantity is L nu, so I'll call it L nu, which is like, again, so L is different from L nu, that is per unit frequency interval, okay, but should not make a difference, divided by 4 pi A prime. You notice one thing, this is independent of distance to the source. This quantity dA dash, this is the amount of energy you are intercepting. So you have a telescope of area A on earth, you are intercepting some energy in a given time dt, given a given time dt, using an area of telescope which is dA from an area on the source which is dA prime, which subtends an angle d omega at u. Okay. So I am able to define this quantity now. This is independent of distance to the source. This I could have gone now closer to sun, could have gone here and defined this quantity. This quantity would not have changed. It's actually an intrinsic property of the source. Right? You can see it's an intrinsic property. Luminosity is an intrinsic property of the source. The area which would have been exposed to us is also an intrinsic property of the source. So this is like something which is independent of how far the source is from you. So this gives me a convenient description of radiation, right? We took a while to get here, see, and it is needed, this effort is actually needed. There are many different ways to say this, right? I use an example from astronomy. There are more formal ways to say this using what I call phase space distribution function, which many of you may not have read about, right? But we'll read. So one of the things I want you to do after all of this is over is to go derive it more formally yourself, okay? I mean, you guys are very good in searching things, right? You can search whatever, you can just go and derive it, okay? Find a more formal derivation than the one I have given you, right? And there are many in the literature, not just in astronomy literature, in the literature of classical mechanics, right? Because basically it's an idea from classical mechanics. How do you describe not just radiation, how do you describe the evolution of the phase space distribution function? But I will leave it be, I am not going to go there. I leave that exercise to you. Okay, so what have we learned?
Sir,
Yes, go on.
so in this case, the intensive properties, intensive quantities are those which are independent of distance.
Yes.
So if they depend on frequency, they are still intensive.
For this case, yes. Right, absolutely. For if they depend on frequency, it's okay. But suppose the body was moving. Suppose this thing is moving, going away from you, coming towards you. Then frequency also alters. Right? Then it becomes a more complicated game. Okay. I didn't want to go there. So there are two cases in which frequency plays, the change of frequency also occurs. So you have to take that into account. One is if something is moving, as is the case all the time actually. Right? So this d nu is not invariant. On the source is different, on observer is different. The other case is the expanding universe, something you may come across. So again, you can make a note for yourself, expanding universe, check specific intensity for expanding universe. There it is not an invariant as it comes towards you, right? So there are cases where it will change, but when the source is static with respect to you, it's not moving with respect to you, then it is an invariant, right? And that's what I proved by very simple geometric arguments, right? So and d nu I've just plugged in there, assuming implicitly, so good you asked this question, that d nu doesn't change, right, as light travels towards you, right? So it will not, This does not change if the thing is not moving, right. So, I have assumed that static configuration. All right. Any further questions on this point? Point is clear? Yes.
You are assuming that the light is incident normally
Incident?
normally on the telescope.
I don't have to assume it. You are absolutely right. I don't have to assume it. Okay. So, in fact, I am going to just give you a geometry in which like such an assumption is not made. Okay, you are right. In fact, okay, I'll just give it. In fact, that was the next thing I wanted to say. What you said, you are right. So, what we assume, the way we define intensity now formally is you have an area dA, right, and area in physics is defined with respect to a vector, an infinitesimal area that is normal to it. So, when I say there is an area, you mean the magnitude of area and a direction which is perpendicular to the infinitesimal area, that is what you mean, right, and the solid angle could be in any direction. So, you see my point, it is not normal, and this is the angle theta, right, which is with respect to the direction on which the solid angle is. So, solid angle is arbitrary with respect to the area. It is not assumed that the area and solid angles are aligned. I have assumed it, but it is not needed in the description, right. So, in fact, that is what we find moments of this, but this is something I do not have time for, right. So, you are right, good point. You notice all these points. So, that is what I want you to note, right. When something comes to you, you immediately say it because I might miss it. I have to go at a certain pace and finish some stuff, right. So, I might miss some of these things. So, this is our basic geometry. We have an infinitesimal area, we have a normal to the area, and we have a solid angle into which the photons are either emitted or they are coming from the direction. Both ways you can see are valid description, right. Either the photon going this way or the photon coming into you, right, is both the same thing, right. One of them will be negative of the other, right. So, intensity is defined. It has a somewhat more complicated definition because the dA, right, it can change when I go from one dA to another. So, it can be a function of distance space also, but I am not going to talk about that. Okay. So, as you study more about this, you are going to generalize these concepts, that is what you will do. So, this is the most basic concept I am introducing you to, but then you will generalize it to other cases. Fine. Now, I have defined it, and I have defined an invariant on the light ray, right. So, my first equation of use is to say if there is intensity, it is invariant on the light ray by virtue of shear propagation. If just propagating, the light is propagating from the source to you, then this thing will remain invariant, right. The ds is the distance. So, now I will just draw some geometry here. So, there is a source here, there is light coming from here. ds is a distance along the source, along the direction of the propagation. Again, ds would be more complicated if the thing was closer to you. You will have to take into account the angle from where it is coming. I am not going to bother about those angles, right. So, ds you can actually take it to be z axis if you feel like, right. In a more complicated case, ds will depend on, right. ds is defined along the ray. It is a distance along the ray, but if I choose a geometry and if it is coming from another direction, the same kind of geometry that we have here, then it will depend on not the simple coordinate system. It won't be single axis, it will depend on other axis, theta between z axis and the z axis and the direction of the propagation of photon. But ds for me is simple. This is the direction of propagation of photon. Along that, the intensity is conserved. This point is clear to people, right. That this quantity that we have defined, right, if you let photons propagate into free space, then this quantity would be conserved on the light ray, right. I can go close to sun and still this quantity is the same, intensity does not change, right. That is why a question is always asked. The intensity of light does not change, but your eyes do not burn when you look at a star, right, far away, but your eyes will burn if you were close to it, right, because close enough it will be like sun. Why is that? Why so looking at stars our eyes do not burn. It is a trick question, but still try to address it.
Radiation also carries
Huh?
Radiation also carries heat.
Absolutely, it does. So you see, that's what I'm trying to say. Intensity, which is an intrinsic property of the source, right? So each light ray that is coming towards you has the same brightness, right, as it was very close to the sun, right? It's an invariant. Yet it doesn't burn your eyes, right? Why doesn't it burn your eyes? When you look at a star, when you look at sun, it does burn, but at a star, when you look at a star, it doesn't burn. Why? Elaborate on the point. Yeah, energy. Yeah, you complete your point, both of you.
Energy intercepted is more when we are closer to the sun. The stars we are farther. There will be
Energy intercepted depends on the solid angle, right? So you complete your point now. Go on.
Solid angle subtracted by the eye is more, it is present there.
You got that point. See, energy intercepted is what? It's I nu multiplied by delta omega. Correct? Correct, no? That is the energy intercepted. Correct? So the point is, what is the delta omega of the star? Of the star? No, it's the eye. So what is actually coming into your eye? So the delta omega of the star is actually much, much smaller, right? So when you look at the sun, what you're intercepting is I nu delta omega, where delta omega is the angle, it's a resolved source. Why I gave you this example is when you look at sun, for instance, energy intercepted is proportional to I nu delta omega, right? Where delta omega is the angle subtended by your eye on the sun, which is a few arc minute. That's a lot of energy. Correct? That's fantastic amount of energy. But when you look at a star, right, star is not resolved. This is not the correct answer for star, because starlight is not coming from all the solid angles into your eye, right? In fact, what you are intercepting is this, d omega prime divided by d omega, where d omega prime is actually the solid angle of the star, right? And what solid angle does a star have on you? Even the closest star is milliarc second, okay? And this is arc minutes, and you have to square the angle. So this is millions of times less. So the energy intercepted is indeed less. It is because the solid angle your eye subtends, eye only resolves sun. It doesn't resolve a star. So you have to be careful with definitions now, right? You understand my point? That's why your eye is not burned, because the energy intercepted is indeed much, much less, right? Because of the fact that, so these notions will keep coming back to you. Something is resolved and something is unresolved, right? A star is unresolved with respect to your eye, but sun is resolved. So using I nu as a basic definition, which is actually the correct thing to do, right? You are able to figure these things out. So this is a trick question. Okay, why doesn't the star burn your eyes, even though the brightness of a stellar of a star is the same? The brightness of a ray coming from the star is the same as that of sun, but it's not about brightness of the ray. It's about how much energy your eye intercepts, because that's what will burn it. And that's much less, and that has to do with solid angle. Okay, good. So, is there any other point somebody wants to make?
How can you find d omega dash?
How can you find?
D omega dash.
We can't find it. So that's the point. So good point again. So yeah, like I said, we have a telescope typically. Okay. Every telescope has a certain angle that it subtends on the sky. You know what that angle is? Rayleigh criterion. Rayleigh criterion. People have heard Rayleigh criterion? Tell me what Rayleigh criterion is.
Spots are said to be resolved with their first minimas of the diffraction just over
Yes.
time.
And what is that angle? So you're right. If there are two sources which are separated by a certain angle on the sky, this is a criterion when you are able to just resolve them, right? But
We want the formula
I want the formula.
0.6 lambda by
Let's forget about 0.6 because that's for a circular aperture, right? So theta is on the order of lambda by, correct? So that answered your question. If you have a telescope, right, of aperture d, This is the angle it subtends on the sky. It accepts light from this angle, right, typically, because this is what the minimum angle it can resolve, right. So, single telescope gives you 1 d omega, okay. If you pick another telescope, it will give you another d omega. So, d omega you know from your instrument, right. So, if you build an instrument, you know how much the angle is that it is accepting light from, it knows it, okay. So, this is a derived quantity. Specific intensity is not a measured quantity, it is a derived quantity. I must know what the d omega of my telescope was to be able to calculate it, right. You understand my point? So, that is how you derive it. But what happens is there are instruments called interferometers which have multiple scales in the problem. There is no singular angular scale there. You can have an angular scale which could change by orders of magnitude, right. In that case, you have to be careful computing specific intensity, right. You have to specify what I am doing. So, you can actually be accepting light from different scales, okay. Does that answer your question? Okay. Any other question? If there are no further questions, I will give you an exercise, and if it's possible, try to, oh, what happened? Light failed. Okay, I will give you that exercise because you should be able to see the board. Okay, it's back. This is sun, okay, sun here, earth here, right. So, let us use earth as a detector, okay. You know the luminosity of sun, you can find it, right. Bolometric luminosity you can find, I mean of over all wavelengths, right. You know the distance between sun and earth, you should be able to find the temperature of earth. So, temperature of earth comes from where? Why does earth have a temperature? It has other sources like radioactivity from within the earth, it has sources, right, but most of it is solar radiation, you know that, right. So, we should be able to compute the temperature of earth based on how much light it intercepts, right. It is the same geometry I have told you just now, right. So, use these numbers, luminosity of sun, distance to sun, and whatever other data you want, right. I am not going to tell you what other data you want, right, but all the data is at your fingertips, you can find it, right. Find the temperature of earth, and I want this answer in the afternoon. Talk to each other, find it. It's very straightforward, it uses exactly the same geometry I just talked about, right. It will be a test of how much attention you are paying in the class, okay. It's very straightforward though, okay. All right, I am done with this, I will move on. So, now let us move on and consider the case when there is something between. So, let us consider this geometry. You have a source which is emitting light towards you. You have another source which can absorb this light as well as re-emit in this same frequency, okay. And this is a telescope. We want to know what is the net impact of this source on what is coming from behind. I mean, what is coming from behind is not even important, we can take it out also later on, right. But now what I am trying to say is we must introduce change in intensity along the light ray. So far we had thought about free propagation. Now we are going to introduce change in light intensity as light comes towards us. So initially it was 0, now we are going to put in some numbers, right. So suppose it is absorbing light, how much would be absorbed? Any idea? Amount of light that is absorbed would be proportional to intensity, incoming intensity. It is minus incoming intensity, and I put a coefficient called alpha nu, which has units of 1 by length, right. As you can see, it is 1 by length because this is length, this into this would be dimensionless. So if light is being absorbed as it propagates towards us, that is what you would get. You will get an exponential fall in the intensity, right. Radioactivity, you have done this kind of things, right, you know this, right. So whatever falls, it is proportional to intensity, and the next moment the intensity has decreased, so there is an exponential solution to this, right? So it will exponentially fall, right? But suppose there is, from this blob of gas which is in the middle somewhere, you also have emission in your direction. Possible? Right? I'll talk about a very specific case later on, maybe in the next class. So you are fine with this equation? It's a very simple equation which is linear, right? It is proportional to, so long as J nu is not a function of I nu, J nu can become a function of I nu. Now that becomes a very complicated equation, and that is possible, especially when there is scattering. So in astronomy, in particular actually, I've noticed in physics less so, we distinguish between what's called absorption and what's called scattering. And everybody keeps using the term, and they never ask the question what's the difference between the two. In reality, there is not that much of difference between the two, right? But I will not go into that debate. If you want to discuss it, we'll discuss it later, right? So for all intent and purposes, I would say the photon is absorbed, right? So photon that is coming towards you, a fraction of it is absorbed. Alpha nu is a property of this, correct, right? Not of the incoming radiation. Similarly, J nu is a property of this. Something is being emitted in your direction, right? We will seek a solution to this kind of an equation, right? Assuming J nu is a constant, right? But before we seek a solution to this, right, we can write a solution. Somebody can tell me how to solve this equation. No, you actually put this on the other side, and you have integrating factors, a straightforward thing, right? I'll write a solution to this, and we'll discuss it. I nu as a function of S. So let's say this is 0 and this is S. Okay, so this source has an extent S. So up to this point, before it hit this blob, intensity was constant, right? Unless you absorb or emit something in that, intensity is constant. So it's 0. So this is the extent of the source, right? You can find, but wait, I will define a few quantities before I write down the solution. Let me define a few quantities. Let me define what is called optical depth, because I am going to use this quantity. So I have defined an optical depth which is an integrated quantity. It's an integral of alpha nu over ds, right? But the integration limit, now that is the most important thing. The integration limit starts from 0, which is here. The photon coming from this direction. This is where the source starts, and S is where the source ends, right? So this is called optical depth. You have heard about the quantity optical depth, all of you. You have not. You have not heard about optical depth? Okay, okay. Is it true of others? You have not heard about optical, so let's discuss this optical depth, right? Optical depth is okay. I did not realize. You are not been introduced. Statistical physics course you did? What courses have you done then? The thermodynamics? Not statistical physics? Kinetic theory of gases? Okay. You haven't read Feynman lectures on that. Have you? What course material do you follow for that? Kinetic theory of gas? Huh? Reef you follow Reef. Reef would have introduced concept like this, okay? But anyway, you will come across this. Don't worry about it if you are not come across this. Let's discuss it. Good. I asked you people and you told me you have not come across this concept. So let's ask ourselves what optical depth is, right? Optical depth, first of all, is a dimensionless quantity, as you can see, right? It is defined as a dimensionless quantity, right? So it is like a probability when it is smaller than unity, right? So it is like this. You have a set of trees and you are in the forest and you have a gun and you are shooting, right? This is the probability of shooting into a tree, because you might miss it, correct? So this is some kind of a probability of interception of photon, right? So when the photon that is coming towards you, if optical depth is less than unity, its probability of it being absorbed is less than unity. But when it is greater than unity, it can be much larger than unity, right? It means the probability is nearly 1, right? So optical depth gives you a sense of how likely it is to absorb the photon as it travels through this blob. The photon is coming from behind, or it can even originate inside the blob and come towards you, right? So the probability is not just photon coming from behind, that is from 0 to S, right? It could well be from S prime to S, right? S prime could be somewhere here. I can draw a column actually to be convenient. This is 0, this is S, this could be S prime, correct? So the probability is that a photon is emitted. We want to know what is the probability that it will reach me. To reach me, it has to cross this S. After that, the source ends, and whatever is here will reach me, correct? So you get that point. Optical depth is a probability, and indeed you can actually see it is a probability, because if you drop J nu, right, what is the solution? I nu is S is I nu 0 exponential of minus tau. That's the solution, isn't it? So this is the probability that the photon will survive reaching you, right? So if it is small, we call the medium to be optically thin, right? That means the probability is high that it will reach you. The one that is coming from behind or one that is emitted within the source, the probability of reaching you is high. But if it is very large, the probability is small that it will reach you, right? So these are the two limits in which we work, right? I mean, we are able to derive analytic quantities within these two limits, but more often than not, optical depth could be close to unity, and then it's difficult to get analytically much other stuff. But anyway, we will work in these two limits and we will get most of the stuff that we want. So what I can do is I can rewrite this equation now, and I will do it here. I just divided the whole thing by alpha nu, right? So you can see d tau nu, alpha nu ds, correct? I just defined a new variable. In this new variable, things look sort of neater, right? What happened? Oh, the battery,
And now it is fine.
oh, it's working now. So maybe in my pocket it got switched off or something. You can hear me at the back, right? So we can give a name to this quantity, and you will see it is useful to give a name to this quantity. This quantity is called the source function, and you will see why this name comes. Then I can, now it's a very simple differential equation. First order differential equation, and I can solve it using these variables rather than those variables. I could have used whichever variables I wanted, right? I write down the solution. You can check it is correct. Here tau nu is of course defined as an integral quantity again, 0 to S prime. You should be able to check it easily, okay? I'll leave that exercise to you. All of you can solve first order differential equations, right? So I'll leave that to you, right? We'll just interpret it rather than like, spend time deriving it, okay? Let's look at the solution. Let's drop this first. This part only comes if there is emission along the way, right? If there is no emission along the way, this part is 0, correct? This is what you would have got if there was only absorption, right?
So that was only for absorption.
Which one? very, very simple statement. If, yeah. What is this? फिर ये चला गया क्या? Oh yeah. You guys are able to hear me, right? Can you hear me at the back? Okay, fine. So I'll keep talking. I think the recording would be harder when I'm not speaking to the mic, but you people can hear me, right? So I'll continue. So if there is no emission, then all that is happening is the source is absorbing. And only the first part of the solution. So whatever is incident on the column of gas, right? By the time it emerges on the other side, it has been absorbed by an amount which is exponential of minus tau, right? Which is the definition of optical depth. Fine enough, that is simple. It is the emission that is a little more complicated. But if there is also emission on the way, we can still solve for it. It's a linear problem, right? So you can actually see what this means. There is emission on the way. What does this term give you think? So you see what is happening is there is photon that is incident from the back, right? As it travels into the medium, part of it gets absorbed, but there is light that is added to it because this medium is also emitting in that, right? So what does this exponential term do you think says? Let's try to derive it. Let me write it more explicitly. You then know what I'm talking about, right? This is minus tau plus tau prime, which is equal to 0 to s alpha nu minus here plus here 0 to s prime alpha nu s double prime, right? Actually this is minus can you tell me what this means? So photon is emitted, right? But as it travels towards us, it also gets absorbed, right? So let's ask ourselves what happens to a photon that is emitted here at S prime, right? Yeah.
It's fine.
हाँ अभी ठीक है. Thank you. So let's ask ourselves what happens when a photon is emitted here, right? When it tries to come towards you, it also gets absorbed, right? The emitted photon. So it's getting absorbed within the medium. There is a photon which is coming from behind, which has to suffer this entire attenuation from 0 to s. But the photon which is emitted inside the medium doesn't have to suffer the entire attenuation. It only suffers a part of the attenuation, right? That's what this factor is, right? So now we understand what we have got. We have got two parts to our solution. One part is whatever is coming from behind will get absorbed, but whatever is emitted inside the medium will also suffer attenuation, right? Because it has to travel a part through it, right? That's our solution. Okay, I will solve it further, but before solving it further, let me pose a general question to you, right? And then I will come to simpler solution to this equation. Suppose di by dui nu by ds is still 0. I have introduced a source in the middle, but di nu by ds is 0. What does that mean? Yes. Do you agree with me? What this means is that whatever is absorbed is emitted. So this medium as a whole is actually neither an emitter nor an absorber. What is that medium called? That's called black body, right? What form of I nu I need to have in the medium, right? Wait, that is correct, but J nu and alpha nu are not so that's the point. What form of I nu I should have? Because you see, now let's get to concepts. Suppose I have an arbitrary I nu, will it happen? It should have a specific distribution. So when I put matter and radiation together, they both relax to equilibrium, and I will show you they don't relax to equilibrium at the same time actually. Those things are different. But there is a configuration, and that's what you are always told about black body. Just put a blob of gas or something in a big box and close it and wait long enough. Nobody told you how long do you have to wait. But if you waited long enough and you open like a pinhole into that enclosure, the light that you would get will have a spectrum which is fixed. Did you read that? What is that light called? That's called black body. Do you know the shape of that? So I have defined everything in terms of intensities, right? Do you know the intensity of black body? And that's called B nu actually. Do you know the form? Anybody? Make a guess, don't worry if you are wrong, don't worry. I mean, the whole point is I just memorized it this morning, so I'm fine. Huh?
It is something 1 over exponential.
Okay, 1 over exponential what? This? Remember this? There are prefactors here which actually change depending on how you define quantities. So there are 3 or 4 different ways in which this is defined in the literature, right? Per unit frequency interval is how I have defined everything. Per unit wavelength is different, right? And then people also define number density, specific number density, right? That actually is different from by factors of C here. So the quantity I have defined, which is specific intensity here, for that, this is the relevant prefactor. Okay, you should check that this has the right unit. What was the unit of specific intensity again? Now somebody tell me. One of you, we defined it just a while ago. What is the unit of specific intensity as we defined it? I wrote it at that point. You're looking back in your notebook. Okay, go on anyway. You look back in your notebook and tell me anyway. One of you. Shout across. Ergs, what is it?
Watt second, that is joule per meter.
Hmm?
Joule per meter.
Joule per meter square or watt per meter square? Per hertz. Okay, so I'll see guys, like, you know, we are old timers, we use CGS units, but anyway, I'll go with you. Watt per meter square, right? Watt is itself joule per second, right? So I can write joule per second, fine with you, right? Per meter square, what else? Per unit frequency. Per, and what else? Per unit solid angle. Correct, everything, right? So this is energy ergs per second, per meter square, per hertz, per solid angle, right?
Hertz is 1 by 6. Cancel.
That it does cancel. When you work this out, it will cancel. Just check for yourself. This is dimensionless, correct? This is h nu, so this is ergs per centimeter square. C square by nu square is lambda to the power minus 2, right? So this actually has units of ergs per centimeter square. Hertz per second do cancel here, right? So you're right. Okay. So this correct unit here, but the point is the way it is defined. There is a implicit solid angle, right? Definition that has gone in, right? Which I have not written explicitly, right? Because there would have been a 4 pi here which I have divided by, right? When you define number density, there are 4 pi factors. So each time you look in the literature, you will find 1,000 different definitions of it. So know the quantity that you are dealing with, right? Derive it first, right? So intensity, this is specific intensity. There is no 4 pi's here. When number density is defined, sometimes it is defined without solid angle. So there is a 4 pi factor sitting here, the 8 pi factor. Okay. All of those definitions you will come across in the literature, but you should know where it's all coming from, right. We are in physics, in astronomy, we are most comfortable with this, okay. Per unit lambda we don't use per unit wavelength. That will change this. There will be lambda to the power 5 somewhere, because d nu is not, you will have to transform that, okay, because d nu doesn't transform into d lambda in a straightforward way, right. Anyway, this is called a black body, and this has a spectrum which rises as nu square at small frequencies and falls as exponential of minus h nu by kT at large frequencies, right. It is entirely parameterized by a single parameter, which we call the temperature of what? What is at the temperature of? That is temperature of photons, right. You may say temperature of gas, right. Not really, be careful, right. This is temperature of photons. So, the statement being made is the following: you have a blob of gas which is right between you and somebody who is emitting, and that blob of gas does nothing, right. It absorbs whatever it emits. That is only possible for some reason. The light has taken the form of B nu, only then it is possible, right. If intensity does not have this form, does it require the matter to be also in thermal equilibrium? There are two different equilibria here, right. I want to emphasize this point more than one time, because you will see why this is true. There is equilibrium, thermal equilibrium of matter in equilibrium with itself, right. You can define a gas at a certain temperature, can you? Can you? Yes or no? Yes. I do not have to define the light that is interacting with you does not have to have this shape, correct. I can define gas in thermal equilibrium independent of how I define photons. This is a description of photon. Or thermodynamical equilibrium occurs when there is no exchange of energy between matter and radiation. That is what we showed, right. For that to happen, both of them should be in equilibrium, right. Otherwise, that is exactly the point. Out of equilibrium means energy exchange will continue, right. Energy exchange continues until both of them have relaxed to equilibrium, right. So, now we have the answer to our question. d I nu by ds would be 0 again when I nu is B nu, right. So, now we have a relation, and let us write it. Alpha nu B nu is J nu. When this occurs, right, we would have the propagation of light through this blob of gas will neither add anything nor subtract anything. Do you know what this relation is called? Make a guess. You have read it. Should. That's it. That's it. This is Kirchhoff's laws, right? I have only probably written it slightly differently. You have not seen this way of writing it, right? Kirchhoff's law was given you as the following. Oh, you know, this is black body is something that emits whatever it absorbs, or absorbs whatever it emits, right? This is what it emits. This is what it absorbs, right? This relation is very crucial for another reason, and actually that is the reason which is not always emphasized, and something I am going to emphasize a little more for you, right. It is that this relation tells me B nu is an intermediary in the game. It is fixed at a certain temperature. This tells you something incredibly important. If I know how something emits, I also know how it absorbs. Does it? Does this relation tell you that? Powerful, right? Very simple. We have done very simple things, but we have reached very powerful conclusions. I know if I can work out how a thing emits, I can also work out how it absorbs, right? You will say, wait, that is in thermal equilibrium only, right? That is only in thermal equilibrium that is possible. But what has thermal equilibrium to do with it? The correct way to look at it is that because a thermal equilibrium would exist, these are microscopic processes, right? And I am going to give you a specific example of that afternoon's class, okay? This is determined by some microscopic process, right? You can have a gas, it ionizes electrons and protons, right? Electrons going past protons and emitting light. You have read about it, it's called free emission, Bremsstrahlung. You heard about it? Wow, very nice. This it's emitting that light, it's coming towards you, right? Now, I can work out J nu for Bremsstrahlung long, right? But if I want to know what is the inverse process, electron going past proton emits, it's electron plus proton plus a photon, that's the light. Now, inverse process is very complicated. A photon comes, is absorbed by an electron and accelerates in the presence of a proton, right? I want to know what their inverse rate would be. That would be the rate at which the photon is absorbed actually. I have it, right? I have it, and it's incredible that every forward process also gives me the rate of its inverse process, right? Why? Because I know that these two processes together have a state in which they would go to equilibrium, right? So, even if they are not in equilibrium, they may not be in equilibrium, this relation must still hold. Is it clear to you? This relation is this is a statement of microscopic processes, you see. Thermodynamics is a statement not of microscopic processes, right? Thermodynamics is a statement of a macro statement, right? But this is a statement of microscopic process. But then you would say, would it be true for all processes? Ask that question. Did it occur to you? Did you ask that question? Would it be true for all processes? Ask it loud. Would it be true for all processes? Would it? No. Why no? Yes. Suppose I have one process in the universe. Would that process allow me to relax to equilibrium? Suppose there is this process, and I'm going to solve this equation. I think like now is the time to stop and reconvene in the afternoon, right? Yeah. So I'll stop now and reconvene at 2 o'clock, right? That time we'll continue this conversation. So you think in the meanwhile and derive that quantity, right? Yeah.
And discussion outside.
Outside.